Today we're going to talk about linear regression and how to solve it using gradient descent, or another type of gradient descent like algorithm called Atom. We will then code out linear regression using Python and NumPy afterwards. If at any time I make a mistake in this video, please feel free to correct me in the comments below. My handwriting is bad. I'm writing with this little pencil tool thing on this computer, and my handwriting is not very good, so apologize for that. Linear regression is a machine learning algorithm that can solve a linear equation. There are non-linear regression algorithms out there that can also be solved using machine learning, but today we're going to talk about linear regression. For example, y equals 5x is a linear equation. Actually, linear, regression can solve equations where the input variables are nonlinear, so as long as the parameters of those variables are linear. So for example, y equals x1 w1 plus x2 w2 plus wb times 1. Linear regression can solve this, and if this was x2 squared, it is linear regression can still solve this problem, because x2 squared can be represented as maybe x3 equals x2 squared. We plug it in here, it's linear. So so linear regression is when the parameters, which are these parameters, nope, this is the parameter, the w, sorry. The w is the parameters are multiplied by independent variable. So for example, it follows the form that the dependent variable is multiplied by a constant. This is a constant. It can also be denoted as b, plus a parameter times a variable. So nonlinear regression can also be solved by gradient descent or machine learning, but we're just going to talk about linear forms here today. So an example of linear regression is given here. For example, we have a graph of housing prices. And y indicates housing prices, x indicates square footage. We can plot a line through these points like the one that I just did. And for example, we could hypothetically write y equals 200x plus 100,000. For example, maybe if square footage was 1,000, if x is equal to 1,000, then 200 y equals 200 times 1,000 plus 100,000, which equals 300,000 dollars for this house. More generally, we can represent this equation as y equals w1 times x1 plus b, where in this case w1 is 200 and b is 100,000. We can think of b as a bias. For example, even if square footage was 0, so if x is 0, then no matter what, so even if square footage was 0, maybe the lot can, still cost $100,000 just for the land. But if B is equal to 0, then no matter what W1 is, when X1 is equal to 0, then whatever number times 0 plus 0 is going to be 0 for Y. So when B is 0, X1, when X1 is 0, Y will be equal to 0. So this graph has to go through the origin like we see here. And for the graph that we just plotted, we don't want it to go through the origin, because when the square footage is 0, the price is still not 0. Because there's a land or something for this example, and it still has a cost. So we want it to move off the origin, like we see in this graph here. There's a bias. So how do we find W1 and B that will make a good representation of this graph to get this best fit line that I've drawn here? We can use two methods, more than two methods, but two methods will be mentioned here, one briefly and one in detail. One is gradient descent, which is a really popular optimization algorithm for deep learning and machine learning in general. And then another one is called the normal equation that is used, that can solve for linear regression, squared errors, like this linear regression problem here, using linear algebra. So we're going to briefly talk about the normal equation, very, very briefly. So I'm going to write that here for this example. So for the normal equation, it's denoted as, this is equation. It's A transpose times A times X star equals A transpose times B. And we want to solve for X star. So A is the input of X variables for our last example, or data. X star is the weights that were array that we want to try to solve for, and B are the Y values. So normal equation is an analytical solution, which means that we use mathematics and formula to derive a closed form solution. We solve this equation and just we're done. Where gradient descent is an iterative method that we'll see later on. So for this example, for the last example, for example, A could equal, so A is just the X data points. A could equals 1,000, and then 1, 2,000, 1, 1,500, 1, 4,000, 1. So X star could equals to W1 and then WB, and then B could equals 300,000, 600,000, 450,000, 1 million. For the equation, Y equals W1 X1, X1 times plus WB times 1. So this could also be represented as just B. So this value right here, these two is this equation, and this 2 is this equation, and this one is over here. So for example, for maybe 1,000 square footage, you multiply it by W1, the bias 1, you multiply it by bias, and you get a number like 300,000. And you want to find what W1 and WB is. So that's a normal equation. You solve it using linear algebra. Put this over here and solve for that using linear algebra. That's all we're going to go into today. We're not going to go any further about that. There is a Khan Academy series about this that goes into depth. That's really good. I've posted a link to it below. So we're going to use instead gradient descent. Gradient descent is a numerical solution, which means basically for us it's going to mean guess and check as opposed to analytical, which basically for us it's going to mean like solving a closed form math equation like this one that you see here. So maybe numerical and analytical definitions are much more precise than what I just mentioned, but for gradient descent and normal equations, what I mentioned applies here. So if you want to correct me on the super precise and technical definitions, analytical and numerical solutions, go ahead. But that's what we're doing here. We either solving this analytically solving this equation for normal equation, or iteratively numerically finding the loss function, finding the loss, finding the gradient, and trying to minimize the gradient iteratively through multiple steps and updates, using gradient descent. So we're going to talk about gradient descent. Gradient descent is an algorithm that you can start with a random number or calculated number for the weights to start with, like 0 or some other number in your neural network. So this is the weights I'm talking about. You can set it to 0 or some random number, and then you're gonna check the error and see how you can update it to reduce error a little bit and update your weights accordingly and repeat. So in neural networks, they will initialize the weights using a precise formula like Xavier weight initialization or something else. But here we're just going to set it the number of the weights to all zeros. So W1 equals 0, WB equals 0 to start with. And that works just fine for linear regression. So we can set up the equation as we saw before. Y equals W1 x1 plus WB times 1, like we see here. We want to find W1 and WB that will have the best fit for the line. And so let's just write another one for this line again. Remember prices and then square footage. We have a bunch of values like we see here. And we want to basically find this line right here. And then the equation is y equals W1 x1 plus WB times 1. So we will formulate what best fit line is. So it's the line that will minimize the mean absolute error of the y values. So take a look at this graph where the current line is the best fit line. The sum of all the absolute differences between the y values and the predicted y values at the given x is a lot smaller than if we had a line like this one, that was a horizontal line. So we can line these little lines up in a line, and we can see that the horizontal best fit line, the sum of the absolute error line, here is a lot bigger than this one. So if we had these little lines right here, so the difference between the predicted and the actual for all of these points, and because that will be our error, and we lined up these little lines here, and this will calculate the error, from the predicted and the actual. That compared to this line right here, from of this horizontal line, right here, and we line all of these little lines up, and so this line right here is going to be a lot shorter than this one. We're going to formulate this loss function that we see here, this representation here, or the function that we want to minimize. We want to make this line as small as possible. We'll formulate it as we want to minimize the mean squared error, which is similar to mean absolute error, because we will have a positive error addition for predicted y's greater or smaller than the actual y. This is also used commonly in literatures such as Angelin's Coursera class on machine learning, and maybe it's easier handled than the derivative of mean squared error. Handle the derivative of mean squared error than mean absolute error. I'm not sure, but we're just going to go with it. Correct me if I'm wrong at any point. So the mean squared error equation that we're going to use looks like this. Y equals 1 divided by n of sigma I equals, it doesn't matter, we'll just say 1 to n of y hat minus y squared. So this is where sigma means sum from I equals 0 or I equals 1 to, depending on your index, to n, or sum over all of the examples. So this is taking the average squared error of all the predictions. This will be yi. This is a loss function. This is a function that we want to minimize because we want to minimize the error. When the error is minimized, this will produce the line that is of best fit or has the smallest mean squared error. We will try to find the weights, W1 and WB, that will give the minimum value, or hopefully close to a minimum value, for this loss equation using gradient descent. How gradient descent works is we first take the derivative of this loss function at our given initialized weights, W1 and WB. This will tell us the slope or the gradient or the derivative of the loss function at the given W1 and WB parameters. For simplicity, we will not use WB for now and only model our equation as y equals x1 plus w1. So we will not use this for now and only model our equation like this for simplicity for now. So the loss function will remain the same as the loss function that we see down here. Oh, actually, sorry, this is supposed to be a loss, or L. So sorry about that. This is a loss function. Yep. So sorry about that. So, yeah, really sorry about that. So y hat is our predicted value. So y hat is equal to w1 times x1 y hat, and where we initialize w1 is equal to 0. That's how we initialized it at the beginning. So w1 is so this will actually form this equation right here. Y equals w1 times x, so no matter what x is times 0, w1 is y is 0. So this is this graph right here, this line that we start off with. So the derivative of the loss function is respect to w1, which is the parameter we want to update, because x1 is constant. Because the x1 values are the real x values of square footage for the data for this example, and w1 is a parameter we multiply the square footage by to calculate the home price. So w1 is a parameter that we want to change to minimize the loss function. So what we're going to do is we are going to calculate the derivative of this loss function with respect to w1 to see how, if we change w1 a little bit, what change is it going to make to the loss. So when we know that, then we can iteratively we can take a step to change w1 in the direction that will change the loss function in a decreasing manner, and we can update w1 there, and we can repeat over and over again until, you know, hopefully the loss is a small number. That's gradient descent. So let's do that here. So remember again, the loss function is equal to 1 over n, sigma I equals 1 to I is equal to n of y hat minus y squared I. This is the loss function, where y hat is equal to xi w x1 times w1. So dl/dw is what we're trying to calculate, the derivative with respect to the derivative of the loss with respect to the weight. That's what we want to know. This is the parameter, that we want to update. So this is equal to 2 to the n sigma I equals 1 to I equals n y hat minus y hat I times x I. This is calculated by using the product rule in calculus, where if y equals to x squared, then dy dx is equals to 2x to the 1. Or more generally, for y equals x to the n, dy dx is equal to ny times to the n minus 1. Actually, this is supposed to be x. Sorry about that. Yeah. So, and then we also use a chain rule where if y is equals to g to the x, then dy dx is equal to dy dg times dg dx. Another way of writing this is dy dx equals g prime of x times x prime. So for the equation above, adding those two rules together of calculus, dl dw equals 2 divided by n times the sigma as I is equal to 1 as I went to I is equal to n, y hat I times minus y I times xi, as we see here, where y hat is equal to x1 times w1. Y hat is an intermediate variable, and w1 is the independent variable, and x1 is a constant because the input data is fixed. So dl dy hat for a given x is so dl dy hat is for a given x is 2 y hat minus y for a given x, right? So for one x, you know, for if one x, we wouldn't use this. We would, the loss would just be like this, because this part is the sum and average. So the derivative of this is, you know, you just take the 2 down to the front and you minus 2 minus 1 here. And then using the chain rule, dy hat dw1, dy hat dw1 is equal to x1. dy hat dw1 is equal to x1, and because the derivative of a constant times x is the constant. So that's why when you combine it together, so we can solve this, you know, when you combine these two equations, you have the equation that we see here. This one. So we can solve this equation with w1 equals 0 and dl dw, where w1 equals to 0, and then, you know, the loss function is going to be let's rewrite this. So let's start a new page. So dl dw1, when w1 is equal to 0, is equals to 2 divided by n sigma I is equal to 1, I y hat minus y times xi, where this is going to equals to 0 times x1. So this will just go to 0. So we cross this out and just say this is 0, and this is xi. So the derivative of the mean squared error, more generally, is dl dx equals 2 to the n sigma I to I equals 1 to I equals n y hat minus y times xi, as we saw. So for example, if we just plugged in some numbers where let's say we have 201, 402, 503, and this is y, this is x1, where the matrix represents y and x1 sample values at w1 equals to 0 for the equation y is equals to w1 times x1 in terms of thousands, where 201 represents 200,000 and 1,000 for the price and square footage. We see in the best fit line, that was drawn before for the example that we did before. So the derivative of the loss with respect to W1 at W1 equals to 0 is, if we just plug this equation in for these numbers, these set of values, is 2. So dl dw1 when w1 is equal to 0 for this data set right here is equals to 2 divided by 3, because there's only 3 points, and then we're going to do this sum, so that's going to be 0 minus 0 minus 1 y1, 0 minus 200, so this could be also, so 0 y hat is so for this example, W1 is 0, so the x is 1. So this could also be rewritten as 0 times 1, because x1 equals 1, but plus 12 times x1, so times 1 plus 0 times 2 minus 400 times 2, and we're just going to continue it here, plus 0 times 3 minus 500 times 3, and we divided everything by 3. So the answer would be 2/3 times negative 200 plus 800 plus 1,500, which equals about negative 1,666. Okay. And so let's remember that. So this is dl dw1 for this set of equations, for this set of data at w1 is equal to 0. let's remember that and go on to a new sheet. So again, from last time, dl dw1 at w1 is equal to 0 was equals to negative 1,666 for the values 201, 402, and 503. And so we can calculate the full loss. We can calculate the actual loss as this. So this is just a change in the loss, and we change W1. So we can calculate the full loss at W1 equals 0 is equal to 2 is equals to let's see here, 1/3 times 0 times 1 minus 200 squared plus 0 times 2 minus 400 squared plus 0 times 3 minus 500 squared, squared, divided by 3. And this number is going to be 400. So I actually don't know what this number is. I'm gonna have to we'll just say it's like, you know, instead of calculating it by hand, we'll just say it's something like 150,000 or something like that. Instead of doing this by hand, or or something like that, we can just say it's around 150,000. I could be off by like a factor of 2 or something like that. You can check the math, see if this is correct, or I'm off by a few factors, but we'll just say it's 150,000 instead of pulling up a calculator and doing this right now. But check my math if it's 150,000. So I'm not sure. I'm not gonna do it on a calculator right now. So at W1, when W1 is equal to 0, increasing W1 by a small amount called alpha will decrease the loss by a factor of alpha times negative 1166. So we saw that here. So the change in loss with respect to the change in weight 1 is equal to negative 1,666, which means if you change the loss, the weight a little bit, you add it, increase the weight by a little bit, the change is going to decrease the loss by 1,666 times the amount that you that the factor in which you change W1 when W1 is equal to 0. So now that we know that this is what we want to increase W1 by a small amount, alpha, is called the learning rate. Alpha is called the learning rate. So if the learning rate is, for example, 0.0001, so if alpha is equal to 0.001, we will update W1 by a number that's negative 0.001 times negative 1,666. Well, generally, the equation that we're going to use to update is W1 is equal to W1 minus alpha times DL dW1. So we repeat this process over and over again until the loss converges or oscillates around a given set of numbers, which hopefully is around the minimum of the loss. Now, for linear regression. Now, for other problems, it's the same as well. I'm pretty sure. Correct me if I'm wrong, but I'm pretty sure it's the same as well for, like other problems as well. Now, like deep learning, neural network problems. Now, if we go back to the equation as before that we used, y equals W1 times x1. So if we go back to the equation as before that we used, y equals W1 times x1 plus a bias term, WB times 1, where we included a bias, how will we use gradient descent to solve for this? So let's say that we had 3 points for our housing graph again, 201, 402, and let's say this time 100 or something instead of 503. And we initialize W1 is equal to 0 and B1 is equal to 0. So let's draw a new graph for that. So here are our points. So we have 201, 402, and 100 and 0. And then the equation is y equals W1 x1 plus WB times 1, where W1 is equal to 0 and WB is equal to 0. Because, yeah, that's fine. But now we have two parameters. So we want to calculate the loss. And remember again, the loss was 1 divided by n, or in this case 1 divided by 3. Sigma as I is equal to 1 to I is equal to n, or 3, doesn't matter for this case. So y hat minus y I squared. This is the loss, squared error loss. Mean squared error loss. Where y hat, so y hat is equal to W1 x1 plus B1 WB times 1. This is a predicted equation. But now we have two parameters, W1 and WB. So we can take the derivative with respect to both W1 and WB to see how changing W1 and WB will affect or change the loss or the derivative with respect to both W1 and WB. When W1 is equal to 0 and WB is equal to 0. We do this using multivariable calculus or partial derivatives. So here's a graph that we're going to try to see what this does. So in this graph, we have a x and a b. So we have so in this graph right here, we have a x and a b. So we could just say actually we have a WB and W1. Sorry about that. We have a W1 and a WB. So for any given point. So I guess right now we're at here. This point right here. When W1 is 0 and WB is 0. So this maps to a number line. Here, and where this number line represents y hat. So this is the y hat number line. So this, equation right here. Where y hat is W1 times X1 plus W plus WB times 1. This will map to another line that is the loss function. Where the loss, again, is this function over here. 1 divided by 3, or n, times the sigma I is equal to 1 to I equals to 3 times y hat minus y squared. So it's just a sum. This is the mean. This is just average. And divided by n is this is just average of the squared errors of each of the values. This is the mean squared error loss. So if we set W1 constant and move WB, so if we set W1 constant and we move WB by a little bit amount, this will make a change y hat. So if you move this amount in this equation up here, this will change y hat by some amount, and we fix W1 as constant. And in turn, this will somehow change the loss, because you plug y hat, which is a different number, and plug it into the loss equation that we see here, and that you see here, and the loss will change. Similarly, if we set WB constant from the origin, we change W1 by a little bit, this will change y hat by some number, and again we'll change loss by some number if we set WB as constant. So we'll change the y hat equation, the number y hat, and then I'll change L. Changing y hat will change L by some number. And if we change both W1 and WB, it will again change y hat by some amount. So if we go from here to there, this will change some amount, and we'll change the loss by some amount. So if we change both W1 and WB, it will again change y hat by the amount that changes B1, by the amount that changing B1 changes y hat, plus the amount that changing W1 changes y hat. We can see that with the equation y equals W1 x1 plus WB times 1. If we change B1 by some amount, y will change. If we change w1 by some amount, y will change by dw times x1. So by changing this amount, we're going to change w1 by that amount. See how it affects y, and then we will add how changing wb by this amount changes y. We'll add those two changes together to get this change right here, and then we're going to add those two changes together to get this change right here. And we can see that right here. So if you change w1 by some amount, it's going to affect y by some number. If you change wb by some amount, it's going to affect some number, and those two changes here are added together for the change in y hat. So we can set wb as a constant and take the derivative dl dw1 to see the change of loss with a change in w1, holding b1 wb as constant, and then we can take the derivative dl dwb dl dwb to see the change of loss with respect to change in wb, holding all others constant. Then, as we saw, we will know the direction and change to the loss function is if we change wb and w1. So mathematically, this comes down to dl dw1 is equals to 2 to the n sigma of I equals n, I equals 1, y hat minus y times dy hat d dw1 and this is going to equals 2 to the n, again I equals n, I equals 1, y hat minus y, times x I. Where y hat is equal to w1 x1 xi plus wb times 1. And because for here, wb is constant. So, and then again, dl wb is equals to 2 to the n, I is equals to n, I is equals to 1, y hat minus yi times dy hat dwb equals to 2 to the n, I equals to n, I from 1 to n, y hat minus y I hat I, and that's it. Because so we use using the product rule and chain rule. We use the product rule to move 2 down and make 2 into 1, and then we take the derivative of this function using the chain rule to get the value here, because derivative of WB, y hat dy hat dWB, when W1 is constant. So this is a constant number, derivative constant is 0, and the derivative of this is just 1 with respect to WB. So you get this function here. So we can then calculate the derivatives or gradients, dl dW1 and dl dWB, by plugging in the y and x values as we did before, and calculate the gradient or derivative at W1 equals 0 and WB is equal to 0. Then, as we see on this graph from before, and we will move W1 by some small amount in a direction that will decrease the loss, and move B1 by a small amount that will in the direction that will decrease dWB's loss that we calculated when we plug in numbers to this equation here at W1 equals 0 and WB is equal to 0. So we use gradient descent for this, and the equation again is the updated equation is before then. So you have this graph here, right? And this is the graph that we're trying to go. And so we have the loss, and we want to update W1 and WB by a small amount that will decrease this loss. So basically, make this amount smaller, right? Because this is smaller. So when we update it, hopefully this will go from this line to maybe like that line, and then it'll go from this line, that line, hypothetically. But sometimes it takes a long time. Okay. So that specific equation is W1 is equals to W1 minus alpha, the learning rate, times dl dW1, and then for dB it's dB minus alpha, which is learning rate, times dl dB WB. So we repeat this process that we did before until the loss hopefully converged at a small number and isn't changing that much anymore from previous to next iterations of this gradient descent update. In the graph, as we change W1 and WB, as we just saw, hopefully the best fit line will possibly look something similar to the best fit line that we had. So from the graph that I just did just now of the iteration of changing W1, WB, how that changes the line to hopefully go to the best fit line or near the best fit line. Alright, so let's code this up in Python. So let's code this up in Python using NumPy. So Oops, sorry. Let me just double check that I'm still recording, because this would be really bad if I'm not recording. Okay, I'm still recording. Alright, so let's just code this up in NumPy using Python. So NumPy is a popular numerical library in Python. So let's create a linear regression class, and then we'll create 3 methods: train, validate, and predict. And then we can have the input data and the XY data be the input data, and then we can put epochs to show how many epoch is just iteration, show how many iterations of gradient descent we want to do, and then set the alpha learning rate. We can just have a class of linear regression, and then we can just maybe say this is multivariate linear regression using gradient descent. We can initialize something, just pass for now. If at any time that I'm coding, I'm sure there's better, faster ways to code. You can leave a comment or pull request. I'll have a notebook link down below, and to make suggestions or pull requests to improve the code. Alright, but this is just one way you can do it. As you know from data structures, algorithms, you can write code faster. Typically, if the code isn't written very well. So, yeah. So let's do that. Make a train. Self XY as the parameters. Epochs, you can just initialize it to be like, I don't know, 100 or something. Learning rate, we can just set it to like, something like this. And then, so this is the X data, and then Y is the predicted value. So now let's initialize X and insert initialize X and insert a bias term. P.insert X 0 1 X is equal to 1. I have this pre-written that I'm looking at because just to make your time better and make this a lot more smoother than trying to get errors that will make this video a lot longer than it needs to be. So this will insert a bias term, because remember, we don't come with a bias term in our graph here. We just have the X values, and then we add a bias as 1, and then we multiply that 1 by our bias weight. It's not part of the inherit X data set. That's why we insert it here. And then we will initialize our weights here to be zeros to the shape of X, to number of weights, to the number of X parameters there are plus bias. So we'll just say for 9 to 1 and epoch, so we're going to iterate like we saw. And we'll just say y hat equals self.weights X dot self.weights. So this is just a dot product of your X values, your input values with the weights. The dot product is just you line up your X values, your X1 values, and you multiply them by your weight values, your W1 values, and then the dot product after is just you sum them up. So it's basically what y hat does. So this is exactly what y hat does. just takes the W values and the WB values, W1 values, and then the weight values, and multiply them by the X values in line, and then just add it up, just exactly like what y hat does. So y air is equals to y hat minus y. So we saw that in the previous equation. We take the predicted minus y, and then the y air is equals to this is just like some Python reshaping that I felt like I had to do to get this equation to work. Size. Alright, so now we calculate the derivative term, which is 1 divided by 2, 1/2 times NP dot average y air times x, axis is equal to 0. So this is just the derivative term that we saw before, where we have the loss, we take the 2 down. This is just sigma right here. Sigma times 1 over n. That's just the sum divided by n is average. And this is just when you have that y hat minus y squared, you take the 2 down to go like this to take the 2 down. So actually I think this should be like 2. Sorry. Great. So then and then you have the inside, which is y hat minus y, which is this y air term, and then you multiply it by your xi. So you multiply it by the x, because the derivative of the inside, you know, the only variable of the y hat inside is the w, the wi. Everything else is constant. That's a partial derivative that we talked about. So the derivative of that, which is, you know, xi times wi, is xi. So you multiply by this x, which is a vector array of all of your x values. So this will give you your partial derivatives, gradients of all of your x values in like an array form. So self-weights equals self-weights minus learning rate alpha times partial gradients. So this is the update that we saw before. We want to, now that we know the gradients, that will decrease the loss. We're going to update it by some learning rate amount. We're going to do that epochs amount of times. Let's just write something like validate, just another method. So probably want to do this first. Check if weights exist. Let's just write that here. So this will just check to see if weights is defined. The only way that weights, stuff that weights will be defined is if we trained it. Otherwise, because it's not initialized. So if it's not defined, then we're gonna say, hey, stuff that weight's not defined, so that means this model wasn't trained, so we should train it. And here we're gonna do the same. We're gonna insert 1 for the bias number, which is just the weight, bias weight times 1, WB times 1. So that's X. Just add this bias 1 number to it. That is going to multiply by the bias weight that we trained it on. Predicted Y equals NP dot X times self dot weights. This is the same. We take the weights, we take the X for each X array, and then we're going to line it up and multiply it like we saw on the Y equation, and then we're going to sum it for the predicted Y that we saw, that we did many times. Okay, RMSE equals NP dot squared root dot NP dot average. So this is root mean squared error. It's very same thing to mean squared error that we've been doing, right? We take the squared error, y hat minus y squared, and then mean it. So sigma, iterate over sigma, sum it, and then divide by 1 over n. That's average. We're just going to then take it and just do a square root it again. So just take this whole thing, square root it. It just makes this square number a little bit smaller. Maybe make it similar or more in line with what the loss values are, because these losses are all squared. So if we square root it again, it makes the loss look smaller, maybe in line with what like with some of the relative to some of the numbers that we might see for like the difference between y hat and y predicted. Alright, but it's just multiplying by a scalar number. You can do mean squared error, but this is just what we're doing here. It doesn't matter. So we're going to average it. So this is just mean squared error. This part by minus predicted y, and we're going to return the predicted y and there. To predict, we're going to do the same thing here. Check if weights exists. We're going to insert it here, the bias. Again, we're going to then just multiply the weights by x that we trained it. We're going to return the predicted y. Okay, so we're going to run that equation here. Alright, so now we're going to run that equation here. We're going to initialize this object, and we're just going to put, just put some random numbers, x, because random 50, size equals 101, it's just random numbers. Now we can just print it to see what it is. Ah, I think this thing died. I have to run it again. Oh, okay, let's just copy this over here and copy this thing over here. this over here. And this thing, copy it over here. Alright. So we have an error here. Okay. Another error. Okay. So we're just going to take our y values and let's just be some random number it correlates yx. You know, there's a lot of ways you can set this up, but these are just the parameters that I use that works for my equation here. That actually works with the sklearn data set, but I'm sure you could write it differently or better. So we're just going to train it. Linear regression dot train. Call this method up here. That is the representation of what we've been talking about this whole time. X, Y, learning rate. We can just put it as something equals 0.001. We got another 0. Okay, epochs, I don't know, just say like 1,000, 10,000, just to make sure it's going to converge. And we're going to just train it and see. NumPy has no inserts. Alright, what about this? Okay, it looked like it trained. So let's predict it in the same, let's predict X using the same graph. Okay, predict missing additional Y. Well, let's just do this. We don't need Y for that. Linear regression has no check weights exists. Oh, they just spelled it wrong. Alright. So now let's import matplotlib.pyplot as plt matplotlib.ml. This is just a graphing library. Scatter xy. So this is the xy point, and let's plot our line to see if it predicted. Ooh, very close. Maybe you need to run it a little bit more. So, I'm not sure why it's doing that. Let's see. Maybe we need to run even more. Maybe if we change the learning rate. That's odd. Okay, well that's pretty good. So, what if I did less? And just made the learning rate better. Okay. So the learning rate, just shows how big of a step you update your weights, and the number of epochs is how many times you update. How many times you take the partial loss and you update. Alright. Now, a problem that we will have is if we change the learning rate, the model could actually not converge depending on the learning rate that we set. If we set the learning rate to too high of a number, then when we multiply the gradient or the partial derivative of the loss with respect to a particular weight, we can update the weight such a large step that it overshoots the minimum of the loss and go all the way to an even higher loss past the minimum. Now if we update the weight again using gradient descent, then the gradient will be even larger in absolute value because we have updated the w past the minimum of the loss function so much that if the gradient of the loss at that w is even higher in absolute value than the previous w. So when we update again, we will update an even larger update in the other direction. So this is called divergence. It's okay if w goes past the minimum so long as the gradient of the next step is smaller than the gradient at this current step. So the gradients become smaller and smaller, and we will converge. So we're going to see an example of this here, and I'll draw an illustration as well. So the learning rate is set to a too high amount. We will see this problem that the gradients are becoming larger and larger in oscillating fashion, and the loss is becoming larger and larger. So this makes our model pretty fickle. So if we have multiple weights and any one of those weights don't converge, our model will diverge, I think. I'm pretty sure it's like that. Tell me if I'm wrong, somebody out there. But yeah, I'm almost pretty sure it's like that. So we need a solution for this to help our model be more stable in training. And we can introduce something called Atom, but let's first look at that. So if we put the learning rate here, our model never converges. Why? What happens? So we see that if we model starts here, and then 2 epochs, our model, our line gets like crazy large, and then it gets so large in the other direction. And in the other direction, and it goes on, and if you just keep going and go on and go on, it gets like some insane number. So why is this happening? Well, it's happening because of just exactly what I just said just now. But we can just try to print this to see. So if we printed the gradients, let's see what happens here. Well, we can take a look here that these are the gradients, that the gradients are getting, starts with this for x, for w1, and then this is b1, and then it gets from this gradient to this super large gradient in the other direction, in the other positive number, and then it goes to super negative in the other direction, right? So what is supposed to happen is if we had a really large, now it's converging. So now it's converging. So when our learning rate is really small, right, we have this negative gradient here, WB, and then this loss, and then we update the step with our loss. It gets smaller, and then smaller, and smaller, and smaller, and smaller, and smaller, and smaller, and smaller until we converge. So we can look at that here. An example. So if this was our loss graph right here, and it looks like this, and you know, our loss equation was 1 over n, what was it again? 1 over n sigma I is equal to n, I is equal to 1, y hat minus y squared. So if we look at our loss function here, you know, so this is for a given weight W1. You know, if we start here, and so where y hat, let's just say, is equals to W1 times x1. So we have a loss function here, and so we have our W1 here. What's this gradient right here? This is a slope. That's the derivative, the dl dw1, you know, at w1 is equal to, I don't know, we'll just say 5. Is this also the slope? So if we update it by, we want to update it by a small amount, you know, because we see this direction right here is the direction to decrease the loss. So we want to update it a little bit amount, until we get here. But if we update it by too large, we can overshoot this. You know, that's why you see on here that the loss is getting, you know, less negative, less negative, less negative. This is a gradient. It's getting less negative. So because this is steeper, and when you're here is less steep, when you're here less steep, going in the same direction. But if you overshoot the minimum by you update it by too large, you update the weight by too high of amount, you move W too far this way, you can move it all the way over here, and now over here it's even a steeper gradient than before in the opposite direction. So we did see that the gradient, if we, you know, change this to like, oops, see here, right, it goes from negative 50 to all the way to 8,000 something, and then it goes from 8,000 to negative 1, I don't know, whatever that number is, and the negative number, 1 million or something, 100,000, negative. That's the gradient, which is this line. And then so since this has such a high gradient, we multiply it by another learning rate when rate d, so W1 is equals to W1 minus learning rate times dl dW1, right? This was the function. Let me just double check. I'm pretty sure this was function. Let me just double check real quick. I mean, I know this is a function, but just super double check. Yeah, sorry. So yeah, so now since this number is even larger, right, this gradient is even larger, we're going to update it from here, even larger step to over here, and now this number over here is like the gradient is way high, and we're going to update it even larger, so we're going to diverge as we see here. The numbers diverge, gradients diverge, and the loss never converges. So that's why you also see that oscillation, right, from positive to negative, like that. So So we need a solution for this. So we need a solution for this, and because this model is really fickle, depending on our learning rate, And to sorry, I'm just checking if I'm still recording, because if I'm not, this would be really bad. So we need a solution for this to help the model be more stable in training, and we can introduce something called Atom. Atom is an algorithm or technique that we can update the weights using the gradients that will be more stable. So we can set a velocity vector that will keep track of the updates before. So for example, big oscillations of positive and negative gradients will average out to a far smaller number in absolute terms. So the velocity vector will just be a running average of the gradients. So if you have a running average here, even though the linear rates, this is exploding, if you do a running average, you take the average of this 8,000 times, plus this huge number, and divided by 2. Hopefully, the gradient is going to be a lot smaller. So, maybe 50, plus 8,000 divided by each other, is going to be hopefully, like a number that's closer to just a smaller number. And there's a way to do it where I know the next number is such a huge number it'll be a primary factor, but there's a way that you can put more weight on the previous ones and put less weight on the current current iteration, so it'll help this to hopefully smooth out. Yeah, so that algorithm right here, velocity algorithm, is called momentum. And then what we can also do is we can divide the update by a number that is the magnitude of the gradient itself to reduce the size of the update. So we try to reduce such large numbers or even really small numbers but stabilize the update absolute number. So we can introduce that. It's called Atom. Now, Angeline does a really good job explaining all the details about atom and momentum and RMS prop. So the dividing itself by dividing the gradient by the square root of the squared is the RMS prop. It's called RMS prop. When you combine RMS prop and momentum, this velocity term is called atom. It helps stabilize these gradients. So we can create something like that and just look at it. If you want more detail, Angeline does a really good job explaining all the math and all the details of Atom. She does a really good job, so you should check that out. Of looking at it. So we will build a class called Atom. And all right, so let's see here. Oh, I think my internet filter is kicking in. I don't know if you guys see that. Maybe it's just me. This. It's getting darker. I don't know if you see that. Okay, so we can create a class called Atom. Class Atom object def init self learning rate equals 0.01, beta 1 is equals 0.9. So this is the beta 1 is the velocity term that we saw before. We can create class called Atom and initialize some parameters here. Then we will create a call method and create a variable called self.velocity that we'll see. So beta 1, so beta 2. So this is for the RMS prop that you divide your gradient by the square root of the squared value. Velocity equals 0. We'll initialize the velocity equals 0. That's the gradient or the velocity gradient, which is the momentum gradient. Square velocities for our RMS prop. So beta 1 is 0.9. That's how much of the previous velocity we want to count, and 0.1, which is 1 minus 0.9, is how much of the current gradient we want to use to update the velocity. Epsilon, that's just a number, just a tiny little constant that keeps the square. So when you do the square root of the squared, it doesn't make sure you don't divide by 0. Again, Angelini does a really good job explaining all the details of that, so you can check out his class or on all the details of all the math there. He does a really good job. Okay, so self.learning rate equals learning rate. Self.beta 1 equals beta 1. Self.beta 2 equals beta 2. Self.velocity is equal to velocity. Self.epsilon is equal to epsilon. Self.square velocity is equal to square velocity. Self.t is equal to 1. T is the iteration number that we're on. I'm just again checking if I'm still recording. That's super important. Okay. Alright, so we're just going to make a call method. So when this method is, when this object is called, it's going to call this function method. Self.velocity equals self.beta 1 times self.velocity plus 1 minus self.beta 1 times the gradients. Okay, so again, we want the weights. Just like before, we want the weight in the current gradient, just like gradient descent, but we're just going to update it differently, like we said before. So this velocity term is an algorithm, also known as momentum. This will hold the current weight velocity of this iteration. We'll create another variable called self.square velocity that will hold the squared velocity. We'll use this as what is called the RMS prop of the equation later, which in itself is a type of gradient descent optimizer in and of itself. So self.square velocity is equal to self.beta 2 times self.square velocity plus 1 minus self.beta 2 times the gradients squared. So this is the velocity, and this is square velocity. So velocity is used in momentum, right? We use beta 1 is 0.9 times the current velocity, and then, or the past velocity. The self-velocity is the past velocity, or the current velocity from the last iteration, and then times 1 minus self.beta, 1 minus 0.9 is 0.1 times this gradient. We're going to use 10% of our velocity is going to be from this gradient, and 90% is from the last gradient. So it's like a running average, or weighted decay, weighted average. The square root is going to take beta 2 times the square of the past square velocity plus 1 minus beta 2, similar like before, times the square velocity. So right here, I guess we use 0.99, so it super hardcore, uses previous accounts, and not too much, only 0.001, 0.01 uses the current gradient for the second. we're also going to do something called velocity corrected. So self dot velocity 1 minus self dot beta 1 times self dot t. And then square velocity corrected is equal to self dot square velocity divided by 1 minus self dot beta 2 self dot t. Alright. So the self dot the velocity corrections you know, they will correct the velocity during the initialization. So for example, during the initialization, the first iteration, self dot velocity is equal to 0. And then so when you go here, 0, it'll be 0.9 times 0 plus 1 minus 0.1 times gradient, which is like, is going to be equal to 0.1 times the gradient. So that's not what we want. And then the second time is going to be like 0.1 the gradient, last gradient, you know, times 0.9 of that plus 0.1 of this current gradient, which makes the velocity initialized to be like really, really small until after many steps further, the velocity, you know, this will kind of catch up. So when we do this right here, it will negate that, right? So in the first iteration of self velocity, let me see here. Okay, the first iteration, self dot velocity will be 0.1 from here. It'll be 0.9 times 0, which is 0, plus 1 minus 0.9, which is 0.1 times gradient. So this will be 0.1 times the gradient is the new velocity, divided by 1 minus 0.9 squared to the t, which is, the t is 1, so this will be 0.1. So it'll be 0.1 times the gradient divided by 0.1, which is the gradient. So this kind of corrects for this velocity initialization here. And same here, it's the exact same thing here for here. Corrects it in the exact same way. There's like pretty much the same, except this term is 0.99 instead of 0.9 and it's squared for this. Alright, so now let's update the weights. Weights minus equals self dot learning rate times velocity corrected divided by this np dot square root squared velocity corrected plus self dot epsilon, which is just like a tiny little number, so this doesn't divide by 0. Okay, so we can see this is a velocity term, right? Times the learning rate by the velocity, kind of like what we saw before. You know, which is weights equals weights minus learning rate times velocity times the gradient, which is we're using the velocity term, and then we're dividing it by the square root of the squared to kind of like normalize it by itself. And then we're going to self dot t plus equals 1 for the iteration for here for the correction, and we're going to return the weights. Alright, now we need to update our linear regression to do that. So here, and there's so many ways you can do this. This is just one way that I wrote it. I'm sure somebody can write it in a better way, cleaner or faster code than me. And if you have any corrections or something, just leave them down below or on the GitHub pull request. Alright, so we can take in an optimizer and we can make that optimizer to be the optimizer, and then for here can just change this to be self.optimizer, self.weights, partial gradients. Then everything else I think should be the same. So let's check it out to see if this is going to work. Oh, missing. Oh, yeah. Now I need to put optimizer is equal to atom. Velocity is not defined. Maybe I spelled it wrong. Let's try now. Another error. Self. Where was that wrong at? Square, self.square velocity. Self.square velocity. Oh, right here. Oh. Okay, let's see if it works now. Alright. So we see that the gradient is getting smaller really slowly. So what if we did more? Is it getting epics? Is it getting smaller? Wow, it's getting smaller really, really slowly. So I mean, you can definitely see that it's getting affected by learning rate a lot less, because this would have diverged by now on the other using gradient descent. Just training. Okay, well, I fit the data. I mean, you can see that it a lot less due to like learning rate, you know, in terms of divergence. Lastly, we're just briefly going to talk about linear regression for non-linear variables. Just real briefly, so the x input could be non-linear if it's data or the variable is non-linear, but the weights and bias, you know, if the weights are still a power of 1, you know, without exponentials or not logs, or anything like that, then actually, let's just skip that. We talked about it briefly, so let's just end it here. So basically, linear regression is when the parameters are multiplied by an independent variable, independent variables. Both linear and nonlinear regressions can be solved using gradient descent. Here we solve linear regressions, but you can have nonlinear regressions where the weights is dependent on the variable itself, so it's not nonlinear. It's not like a independent parameter multiplied by independent variable multiplied by a parameter, and the variable does not depend on the weight. So x does not depend on w1. It just multiplies it. It's not like w1 to the. It's not like x1 to the w1, where the w1 is inside of the x1 function in and of itself. That's nonlinear regression, but it still can be solved using gradient descent. That's it. We're just going to stop there. Put corrections down there if you have any corrections below, or code suggestions on GitHub link. Thank you. God bless.